welcome to my workshop. Today I've taken a delivery from Dell, a 3D printer. It's in kit form and it's a Anet A8 from GearBest. So we'll unpack it and see what we've got to do to put it together. Yeah. It looks like they put an adapter plug in for Australia. It's a good idea. Well, everything is very well packed and very methodical, and by what I can see, everything is very well made. So I suppose we'll start with the superstructure and start making a bit of framework here. I think the hardest thing about this job actually is peeling the damn paper off these acrylic plastic parts. Everything seems to be fit together pretty well. I believe that there is instructions how to put this together on this drive, but you can actually get it on the net. They actually provide it on the net, and it tells you stage by stage really what to do. Like you see on the bottom of the screen there, it says screws 3mm, 18mm long. There's 35 parts and say 3mm nuts. Well, it actually tallies up with what they packaged. So these screws and nuts put this together. I mean, it's very simple really, I think. If you've got big stiff fingers like mine, what you need to do is get yourself a little tool like that, catch hold of the nut, and I've actually found it a lot easier if you put all the nuts in first, like this, then put your part on, like so, and then put your screws in. Much easier process. Right on. Well, there's the superstructure put together. There's only one crucial measurement that I can see that needs to be accurate, and that is the distance between the back edge here and the front edge here needs to be parallel. And in my case, I've not only is it got to be parallel, but it's just got to pinch these bars from slopping back and forth. Otherwise, when the carriage goes back and forth on here, like so, it's going to make these rails move back and forth in the plastic. It's going to wear the plastic away. Then it's going to become not very accurate. So I've worked out that this needs to be 380mm dead. Obviously both sides to make it nice and parallel. That's the only crucial measurement as such. Everything has gone together without a hitch. It's, well, everything's okay. so far anyway. I suppose the telling of how good it is going to be is when it starts turning out parts. Having said that about parts, there was one part here, if I can find it. There's a couple of 3D printed parts here. Now this is the main bearing block, I suppose you'd call it, that holds the x-axis. They're okay, fine, not a problem in the world. However, the little fan nozzle, I just hope that that is not a sample of this 3D printer's job. I would say that's been printed without being cooled, you know. It's a bit misshapen and a bit ragged on the inside, so we'll put that down as a mistake. I mean, look, it's really not a problem. I can soon print one or even make one up on the CNC. It's not a problem in the world. We can probably design something a little better than that, but so far that is the only thing that I have found that could be better. Everything else is okay. Hopefully, I think I've seen on the internet that people say that it's somewhere between 5 and 8 hours to assemble this. Now I've been doing this since 3 o'clock this afternoon. It's now 8:15 in the evening, but I've been called back and forth to my office, so I've only been sort of on this, I'd say, about an hour so far building this. So 5 to 8 hours, depending on your level of ability, is probably pretty fair. So we'll continue with it anyway. Okay, so we've got this far. A couple of things I'd like to point out. First of all, my kit is a more modern kit than what you actually see on the video that they provide, actually on YouTube and on the memory stick, to show you how to put it together. Mine was provided with just standard screws, which I didn't like, so I provided my own Allen head screws. A couple of things to watch out for here as well. Now you see in the video they have the stepper motor with the wire cluster down, and they actually bolted on there like that. Well, you can't. Whether they've changed their motors, you have to have the wiring plug and that pointing out through from the front of the machine, because underneath there, if I can place it there like that, this interferes with this plug, so this is the only way you can put it on. And the next more important thing to look out for is you don't over tighten this belt. This belt can only, when you actually, let me roll this up. When you do this part, putting the belt into these clamps here, and when you tension this belt to put this section, do this clamp up here, you shouldn't have any more than approximately between 1 kilo and 1.5 kilos of pulling tension on it. Otherwise, what happens is it strains this motor out of line, and that could cause problems down the track a little bit. And I dare say it would bowl this in too, bowl this in if you put too much pressure on it. So that's what I found, because they don't tell you these details. They don't tell you how much pressure. Well, I can tell you that between 1 kilo and 1.5 kilos, that's in this direction, is more than sufficient for a little device like this. Another thing, you've got to make sure that it does move freely, like the tension. I mean, you're turning the motor and everything as well, but the tension of it remains the same all the way through, which in my case it does, luckily enough. Also, what they've changed, this is now an aluminium H plate, and I haven't got to that yet on the video, but they used a acrylic plastic one originally. They obviously had problems with that, and they've now reverted to an aluminium. Probably too much flex in it. Okay, so this is the build so far. I haven't been on this full time because I had other things to do, but all told, I've been on this about between 3.5 and 4 hours. It's not a bad build. It's pretty straightforward. There's a couple of little things that you should probably be aware of. One of them, if I can point it out to you. Okay, these little limit switches here, the holes that are in this piece of plastic that attaches to this main backboard here are nearly the same size as the screws that fit in it. So when you go to screw them into it, they strip out immediately. Very, they even just push in on some of them. The only one that actually works as it should is the X-axis one. That screws in to the smaller holes in there absolutely fine. But the other two, of which this being one here, yeah, one there and one here. So what I've done to fix it, it's an old trick I learnt years ago actually, because this is plastic, and you can't put anything too hard in there to fill the hole up. You can't glue it because you want to be able to move it slightly. You need to put something in the drilled hole that will allow you to tighten it up without splitting the plastic. We'll just cut off, and you will need a solder. You will need solder and a soldering iron. This is a soldering iron here. I'll show you how to use that in a minute. Now then, if you just cut off about 1/4 inch, put in each hole, put the switch on, and then screw it in. I think I might be able to, without disturbing too much. This is getting quite heavy now actually. Okay, underneath there you'll see these two little metal things? That's the lead poking out the bottom. Well, what I've done is I've just put the lead in there to take up the slack, as it were. In other words, give something for the screw to bite into that isn't going to split the plastic, and it works fine. Just be careful. There's a couple more serious problems, which are health issues, I would say. This mains 240, 110 volt, depending on where you live. Lead that is supplied with the unit has an adapter plug for Australia and probably other countries. Do yourself a favour and chuck it in the bin, because it doesn't have an earth. This machine definitely needs earthing. So what I've done is, off one of my old computers, I've just cut the plug off it, and what I'm going to do is a process of tinning. Now what that is, you see you've got the fibers of, the metal strands there, and you twist them together after peeling the plastic off the outside. You twist them, but a lot of people, including electricians, just put these bare wires into these connection blocks, which is another subject too, and squeeze down on the wire. Well, that's not very good when you're talking about electrical current, because what happens is you make contact with the outer layers, but sometimes over time the inner layers don't have any contact. So that means you get what they call high resistance, and it starts warming up, and it can give you a bad connection. And when you're talking about electronics, because that is going to eventually supply these electronics, and certainly the processing chip there, can cause you problems, and it could make it fail. So what you do is you make this one solid mass by melting solder, right, into the whole bit of metal copper there. You make it one big strand just here where the connection is. Now then, bring your attention back to, we're going to do two. This is 240 AC. This is the supply that comes out of this device. This changes it to DC. I think it's 36 volt in this case. Yeah, 12 volt. DC comes out of here to supply the electronic pack, the readout, and also these stepper motors. The stepper motors are run off these units here. They're the little controllers, but this is all DC, direct current. All electronics work on direct current, not AC. So yes, I won't go into that any further at this stage, but I will later date. Now then, the health issue. There's two health issues here. First of all, we've just dealt with one. We've chucked away the mains lead that's supplied with this. The second one is this unit. Now, although there's a little cover, little plastic cover here that covers those, you're dealing with 240 mains voltage going straight in here. This is, you know, even with that closed, it's possible that a child could touch this with their fingers, because they're inquisitive little devils, and, you know, worst case scenario, it could kill them. Now we're going to deal with this. Really what it needs is totally enclosing, but it needs cooling as well, but we're going to have to put a cooling fan on it. Right, so this is the process of tinning. Right, so you get your soldering iron and you make sure it's nice and up to working temperature, nice and hot. Melting a bit of solder on it. In this case it is. Now this is the process of tinning. So what you do, actually I'll change hands so you can see. Get the soldering iron and put it for a period of time on the wire, just touch it on the wire. Apply the solder. You'll see it flow through the wire in a minute. There we go. There you go. That one's done. So what you're doing, you're making all these individual strands of copper into one. Just like that. It's a very easy process, but it guarantees you a good joint, electrically. Okay, this is especially important with these DC main power. 12 volt DC wires. It'll take a bit longer because they're a bit thicker. See how it's made into one strand now of metal, not many strands.